We're going to apply Kirchoffs rules to solve this circuit. This is a homework problem. And the reason why you need Kirchoffs rules instead of just using equivalent resistance is because there are two EMFs. So if this wasn't here, then we could just solve that by adding 22 and 18 because these two are in series. But the presence of this changes things. So the first thing we want to do is look at the polarity of the batteries. This is plus and this is minus. And so that's going to be trying to push current this way. And then this is minus and this is plus. So it's going to be trying to push current this way. But the currents won't be the same because of this junction. So we use subscripts to indicate the difference between them. I1 and, well, this is V3, so let's call that I3. And then I1 comes around. And so I1 is approaching this junction, and I3 is leaving this junction. And then I2, we don't know. Is it going this way or is it going this way? So I'm just going to take a guess. I'm going to say, all right, I think it's going this way. Now, if I'm wrong about my guess, I'm going to get a negative number for an answer. And that'll tell me the current's actually this way. All right, so that's what we did for starters. We took a look at the polarity of the batteries, and then we made some assumptions about current flow. Now, the junction rule is really just conservation of matter. Junction rule. So like I said, it's not anything new, it's just conservation of matter. So we have this junction and charges are coming into the junction and charges are leaving. And there's not like parking spaces in here or anything like that. So whatever enters also leaves at the same time. So for the junction rule then, it's just like a traffic light. Cars, the number of cars in equals the number of cars out. And if that's not true, then you've got a problem. So I1 enters, and so that's got to be equal to the sum of the currents leaving, which are I2 and I3. Okay, now loop rule. The loop rule means we can go around a loop that we see any closed loop and then add up the voltage gains and the voltage losses, and those should sum to equal 0. So that's really nothing else besides just conservation of energy. So now here we are, this physicist named Kirchhoff, and we'll be saying that name for hundreds of years. And all it really is conservation of matter and conservation of energy. So, you know, come on, that's not really that outstanding. And then we have to say her name for the rest of eternity. You know how hard it is these days for a physicist to get something named after them? Yeah. Anyway, I'm not bitter or anything like that. All right, so let's look for loops. Here's one loop. We can go all the way around the outside. We can follow I1, and then we follow I3, and then back to I1 again. You might say, well, what about this stuff? We'll get there. But this is definitely one closed loop. And so I'm going to call it loop A. So for loop A, we go around and we sum up all the pluses and all the minuses. So we have a gain here of +9. And then following around, nothing, 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 nothing. And then another gain, so that's +6. And then nothing, nothing, nothing. And then a loss here. And the loss, the voltage loss, is going to be I times R. And the I we're talking about, we're in the realm of I1 here. So this will be minus I1 times 22 ohms. And we're back to where we started. So that should be 0. Now let's find a loop B. Maybe, so for any circuit like this, there are going to be 3 loops actually. So there's the big one all the way around the outside, and then there are little ones like the sub loop and the upper loop, and I'll call that B. And then there's another sub loop down here, I'll call that C. I drew all of these counterclockwise because it's based on the direction of current flow. If the batteries were reversed in polarity, then they would probably be clockwise. So for B, I'll start off at the 9 volts again. So plus 9. And then I have a loss here. So there's a resistor. So that's 18 ohms times, and I'm in the realm of I2 here. So that's a loss, so minus I2 times 18. And I keep following along. And now up here, I'm in the realm of I1 again. So that's minus I1 times 22. And that's equal to 0. And now for loop C, when I come around, I can see that actually we have a problem here. So I can go plus 6, but then I'm headed upstream against I2. So I'm not going to use that loop because there's a conflict. Doesn't matter which way I go. If I go clockwise instead of counter, I have a conflict with I3. So I'm just going to write conflict with I2. So that one's not going to work, but I have 1, 2, 3 unknowns and 1, 2, 3 equations. So I've got enough information to proceed. Now, algebraically, what's up here? Well, it's a challenge when you have 3 unknowns. I have 2 variables here, I1 and I2, and I could solve for one in terms of the other. It might help. Here I can actually just solve for I1. So that's great. I could do that, substitute that value in here, get I2, and then use this to get I3. But I wanted to show you a more sophisticated technique. Here, I'm going to bring all the i's to one side of the equation, all the constant terms to the other. So from the junction rule, I get I1 minus I2 minus I3 is equal to 0. Okay, so I'm developing my system of 3 equations. Right, so I just took this one and rewrote it. Now I'll take this one, 9 plus 6 is 15, and I1 times 22. So I'll put all the i's on one side, so this will be 22 I1 plus 0 times I2 plus 0 times I3, and that's equal to 15. And then for this equation, well, just 9, okay, now I'll move these to the other side of the equation. So that's going to be 22 I1, and then 18 I2, and plus 0, and that's all equal to 9. So now I can turn my attention to an online tool. There are a couple of different ways to do this row echelon method. Kramer's rule is another way. These are all sort of part of linear algebra, but it's the 21st century, right? Checking, yeah, 21st century, good. And I'm going to share my screen, and online there are tons of useful tools. So here's one of them. Yeah, it's just a 3 unknown calculator. And what I've done was, instead of having I1, I2, and I3, I have X, Y, and Z. So I entered my coefficients right in here. This looks like a matrix, right? So there they are. 1, -1, -1, 0, 22, 0, 0, 15, 22, 18, 0, 9. Right. Okay, so let's go back and see what we have for number. So the solver says, down on the bottom, it says that I1 is 0.68. And it says I2 is equal to -1/3. Okay, so we were wrong about that one. Actually, the current goes in the other direction. And then I3 is 1.02. Okay. So let's go back and take a look at what we've got. Right, this is if you add I2 and I3. So you take this number and you subtract 0.33 and you get 0.68. That works. Okay, now, as I mentioned before, I could have done the algebra by hand in this case, but as soon as a resistor shows up on this bottom leg, the answer is no. I mean, it's still possible to do it by hand, but it could take you it could take you half a day. So don't hesitate on a quiz or test if you have to evaluate something like this, to go ahead and use an online tool to get you there. Good. So I hope this was helpful, and I hope you have a great day.